So, very good morning to all. So, as Madam mentioned, the title of my talk is Semiconductor Technologies for 5G Communication. So, it's we can say two different domains. One is semiconductor technologies, and other is 5G communication. So when we discuss the semiconductor technologies, we deals with the semiconductor materials, devices, and their application part. And when we say these semiconductor technologies for 5G communication, then we say these semiconductor material devices and circuits, how they can correlate with the applications in 5G communication. So actually in any type of electronic system at the back end, we require the devices, and those devices are nothing but fabricated with some materials. So in this talk, I will start with the very basics about introduction to 1G to 5G, how the technological development take place in the 5G. Then what are the various type of materials are there, those are used for the 5G application. So there are huge challenges and opportunities in the 5G. So some are the challenges related to material, how we can migrate from to 2G, 3G, 4G to 5G, and opportunities obviously are there for huge speed and so many other benefits we will discuss in the upcoming slide. Then I will discuss briefly about the 5 semiconductor devices. So we will see in the there are as you know, semiconductor devices are mostly silicon based devices are there, and they belong to group 4 of the periodic table. But silicon based devices, they work for the low frequency application. When we talk about the 5G and communication application, then we require the devices and material for those can work for the high frequency. So 3-5 compound semiconductor materials are there, those can work perfectly for the high frequency application, and we will discuss briefly about the 3-5 compound materials and their devices. Then if time permits, then I will discuss briefly about the device modeling, and I will conclude my talk with the summary. So let's start with the very basic historical development of various communication technologies. So some of my slides are very basics, and you might be already aware about the things, and if you feel it's too basic, you can interrupt me. I can skip and move to the next, and if you feel it's you have any query related to, you can also interrupt me during the talk. So I feel it will be better if you make it a interactive talk, and whenever you have a query or your own opinion on the point, you can discuss and you can interrupt for the discussion. So first we start with the 1G system, where that was launched in the 1980s, and that was totally a we can say analog type of system for communication. And actual we can say the communication started with the development of 2G system that was launched in 1991, and where the digital signals propagation start. In that the technologies like GPRS and as technologies they started playing their role. So when we talk about the 3G, so 3G technology, where the frequency of transmissions keep on increasing, and that is more than 1 gigahertz from, and that is quite higher as compared to the 1G and 2G. And because of that high frequency, people can work for the ultra low loss in the transmission and dielectric material, both having the analog bandwidth. So and in this the digital band is near the 2 gigahertz. So if we see the trend of various systems from 1G, 2G, 3G, 4G, one common thing is they are trying to improve its frequency, how we can enhance the frequency. So with the enhancement of frequency, the obviously the speed of a any type of transmission will be high. In the 4G, when it launched in 2011, it was a tuned, and it was a mixture of you can say metallized ceramic dielectric rod, as well as with the various filters that was designed in the 4G. They can attenuate some of the unwanted signals. So in the 4G, the frequency or that was 700 megahertz to 2.7 gigahertz, and this is the we can say current technology we are using, and various applications we can involve, like Internet of Things, IoT, and other automation, communication, uploading speed, downloading speed, all the things were improved with the 4G. So the upcoming 5G is having so many benefits of as compared to the previous one, in term of the its speed, data rate that may be 10 times faster than the 4G, and the latency is almost zero, means the call drop. So although the call drop in the 3G and 4G is also negligible, and mostly in the era of 1G and 2G, we people are having the call drop. In the 3G, when there was only audio call, then that problems was there because of the centralized system. But once decentralized system started, so call drop is already negligible. But in the 5G, the call drop is almost zero. And other benefits of 5G in term of 1000th time of number connected device can be connected together, as compared to the 4G. So this is the application development of wireless networks, where we have different technologies: 1G, 2G, 3G, 4G, and various applications we were having that are related to its throughput and capacity. With the every new system, 1G, 2G, 3G, 4G, 5G, or upcoming in the future 6G is also in the research. So in the any upcoming or previous, the main focus was how we can integrate more and more number of devices together, with having a new features in term of its performance. So the various applications in these are in like digitized logistic, smart home, robotic surgery, virtual and augmented reality, smart retail, health care system. So healthcare system, you can see how improved with the specifically in this pandemic situation. You can see the remotely nowadays doctors are providing the assistance to the patients. So that have help that was done because of these 4G and 5G type of systems. Then autonomous vehicle with the 4G also, in the Germany they were launched driverless vehicle, but there are so many challenges are still there related to the obstacles coming in the on the path, but they can be rectified further with the help of 5G and upcoming technology. Then the precision agriculture is another area where the role of 5G will be huge. So agriculture is not only that the traditional thing nowadays. In the modern agriculture, there is huge technology involvement, from spray of various pesticides on the crop, to picking the fruits and vegetables, and other things like identification of a disease, and other insecticides in the crop. All those things are nowadays monitored with the technology, and definitely the role of 5G is huge in that also. So this is the next evolution of 2G to 4G, how various features add up, take place in the every new network with the advancement. So as I discussed, in the 2G launched in 91, that was proposed in the Finland. Then 3G with the other upcoming features like universal mobile telecommunication, system they have launched this. Then 3G, that is also a IP based service, instead only audio, video also started, but the streaming take place a huge time. So the requirement of a real time video was not able to capture, but with the 4G, the real time videos can be handled. Then the transition from 3G to 4G have been take place with the bimax and LTE type of technology, and they are also 4G is also IP based, where the telephoning, gaming, high definition mobile TV, cloud computing, all those things are involved. So when we migrate from 1G to 4G, or 2G to 4G, the some of the common features that and technology involvement is, we can see the frequency or bandwidth that is keep on increasing from this is for 2G 580 sorry 850 to 1900 megahertz frequency, and bandwidth is 200 kilohertz. Then 1.8 to 2.5 gigahertz for 3G, and 4G is this one. So this is the radio access, how different type of a system used for the radio access, time division, multiplexing, frequency. So CDMA, WCDMA, wide CDMA. So then of DMA, MIMO came in the picture. So this MIMO, multiple input, multiple output type of system nowadays play a major role in the 5G. So we will see in the upcoming slide that the frequency in the 5G is going to be divided in the two different bands. One is 3 to 6 gigahertz, and other is 28 to 29 gigahertz. So the initial phase of 5G will be very closer to the 4G, and because the infrastructure requirement in the 5G is totally different from the 4G. So totally change in the infrastructure in term of towers, or mobile phone, or other things, they cannot replace immediately. That's why you can see 5G is from the research, or from the news, or publication from last 1 decade, but actual implementation is delayed. So it was supposed to be implemented in 2020, but due to some pandemic situation, some delay is there, and other delays because of the huge infrastructural changes requirement is there. To mitigate this challenge of 5G infrastructure, they divided the band in the two group. The first group is 3 to 6 gigahertz, and that is comparable, or you can say some of the infrastructure of 4G can be used for the 5G also. So MIMO is the one of the technology for antenna communication that can you can say integrate our 4G and 5G together for the high data rate and switching speed. So let's come to the 5G. So when we talk about the 5G, 4Gs are already have so many benefits, but the 5G, there is improvement in term of high carrier frequency, wide channel bandwidth, then higher connection density, so shorter latency and greater throughput. So these are the benefits we will have in the 5G. At the same time, the network is expected to be having 100 times faster than the 4G, and the download speed could be eventually reach 10 gigabits per second, and that is quite high speed as compared to the 4G. Then these are the benefits, and at the same time, if we are getting something, definitely we have to lose something in terms of money or cost. Then the money or cost involved in the 5G infrastructural development. So some of the companies like Apple, Huawei, LG, Motorola, Samsung, they already have released their 5G phone, because in the mobile handset itself, if we have to use the 5G technology communication, our handset must be having that facility. So some of the companies, they already provided the their facility in the network. But only the handset replacement is not enough. The other replacement in term of their antenna and a transmission system, that is also required. So 5G network are still expected to be launched in the in upcoming very short time. But for that we have to be ready, keep our infrastructure. One of the infrastructure point of view is the antenna. You saw the towers we have in the 3G and 4G for transmission, they were placed quite far from each other. But in the due to the high frequency bandwidth, the bandwidth reduced, and there you can see their uh, transmission capability, distance carrying capability of the carriers, that is going to be reduced. So we require the multiple towers nearby instead of having the towers farther away. So for those we have to be boost our technologies in such a way we have the access of the transmission. Although 5G is quite fast in term of if we have the local host repeaters are there. If we have to download of or upload the data, video streaming, gaming, high end, high definition streaming of live videos at very high resolution, that is possible. But the when we talk about the transmission from one place to the other, then the tower to tower distance is reduced from 4G to when we coming to the 5G. So infrastructural in term of tower is also required to be changed. Then these are the some of the features. Any question till now? Any of the participant have a question? Or we continue?
Yes, sir.
Okay. So the some of the features of the 5G, as we are discussing, its capacity is going to be enhanced thousands time. Its peak frequency is going to be data rate that going to be greater than 10 Gbps. Then its use frequency, its spectrum efficiency, its mission critical in terms of its latency that I'm discussing. It's going to be nearly zero or less than 1 millisecond. So it's a high reliability, high availability. So many benefits, features are there in the 5G. And you may be aware, you are already attending this course from last 5 years, and you are, some of faculty member may be teaching this course. So I hope all you are aware about these basic things. So let me discuss this 5G, how this is different from the 4G in terms of frequency. So from, as I discussed, from 1G to 5G, one common thing is we are keep on trying to increase the frequency so that the speed can be enhanced. So in the 5G, the two bands are there. One is 3 to 6 gigahertz, and that is a low frequency band, and second is the high frequency band, that is the 20 to 100 gigahertz. So these first band, low frequency band, that is compatible with the 4G, mean some of the infrastructure can be shared. So once our we shift fully to toward the 5G infrastructure, then we can say we will launch totally 5G with the new frequency 20 to 100. Although here the frequency range is 20 to 100 gigahertz, but we will see in the upcoming slides, whole this frequency is not used for the 5G because of the some attenuation and propagation problems are there, some challenges are there. So from this 20 to 100 range, still USA, they made the standardized prototype for this. We can use only 28 and 39 gigahertz frequency for 5G. There are some reasons why we have fixed 28 and 39 gigahertz only. Why not fully 22 gigahertz? Another one question coming in the mind is, if the frequency is only the criteria with which every new communication system have a huge benefits, then why not we are jumping previously directly from 3G to 3 gigahertz to 6 gigahertz we are applying. Why not we are jumping directly to the high frequencies like 39 or 20 gig? One thing I already discussed, the infrastructural change requirement. Second thing is related to its material and devices and hardware requirement. So like we will discuss in the upcoming slides, the material like silicon is mostly used in the previous hardware design in the 5G, like amplification, attenuation, it's filtering, so many things are there. So those, the material have different behavior at low frequency, and same material behave different at the high frequency. So their tuning or compatibility from low frequency to high frequency, that we have to understand, and we have to migrate accordingly. So we cannot jump directly from low to high. We have to jump in some steps so that we can tune our devices, circuits and system with this upcoming frequency.
Sir, the frequencies from 7 to 19 gigahertz, are they already occupied, or occupied by
No,
any
no.
other?
Yes, yes, they are occupied, but the thing is, there are actually different way of propagating. So if you see this particular slide display right now, millimeter wave frequency is required for the 5G. So previously there are different way of propagating the waves. So yeah, as I mentioned, in the 5G there are two range, 3 to 6 gigahertz and 20 to 100 gigahertz. But out of this also we are using this 28 and 39 gigahertz. Why this frequency? Only because the in this frequency the attenuation of the signal is minimum. So I have one more slide on this later on, how different attenuation, like in the 5G major challenge is the signal degradation with the collision of nearby other devices. Like if the hills are there, if even the crops, buildings nearby other, even the air medium, our if rain is there. So because of those environmental factors, the signal degradation is huge. So if we have localized network in a single building, then there is no problem for uploading and downloading. We can has huge speed. But the problem comes when we have to transmission from one city to the other for the long distance
Long
communication. then
distance.
then
Long distance.
then we have to make this repetition in the antenna or towers, or this multiple MIMO system is there. Yes, you have a query, another query?
No, sir. Okay, sir. Thank you.
Okay. So in the 5G we have to migrate to the millimeter wave, where the this is the key technology for 5G. And this with the millimeter waves, our devices and material, those are working in the low frequency, they will not suitable, or they cannot work at the 5G. So that's why I'm saying we have to change the infrastructure first, then we have to think about how we can migrate or implement the 5G. So the but the 3 gigahertz frequency to 6 gigahertz, that is closer to the 4G range, that is 2.7 gigahertz, and the migration is easy. That's why they divided due to the huge challenge, they divided in the frequency range the two segments, so they can initially take the benefit of millimeter waves for high speed and data rate. And later on, once that we are ready with the our infrastructure, then we can migrate fully. So there are some other requirement from the 5G point of view, that is related to in the antenna also there are huge changes are there. Like no early days, the different our even our mobile phone, if you see in the previous mobile phone, there is a antenna at the top of our mobile phone. but in the smartphone there is no antenna visible at the outside, but in the mobile phone itself we have microstrip or micropatch type of antenna, and they are directional antennas. But in the MIMO multiple input multiple output antenna, as I mentioned, the infrastructure in terms of replacement of power is huge. So these MIMO antennas, they will help us in the coverage of large distance, because they are not directional in one direction, but they are propagating signal in the all direction with the having multiple we can say multiple frequency signal input and multiple at the output. So from material requirement point of view of requirement for the 5G, early days when the copper wires were used to transmit the signal from one place to the other. So you see the how the transmission communication take place in the landline phones. So huge call drop and problems are there. Then once from copper to be migrated from optical fiber communication system, then there is the in the 3G and 4G, then there is a huge we can say drastical change in the communication. And as that there is a drastical change from the metal copper to optical, such type of drastical change no will be coming with the 5G. But to take that benefit of that migration from 4G to 5G, we have to prepare our peripherals and systems with the diversible materials. So what are the materials are there, that we will going to discuss in the further. So this is the various material need for the 5G. So we have a base station, we say, from where we have to transmit the signals for the various applications. So for transmission we require the antenna for their protection. So thermal management is also one of the aspect, because as we keep on increasing the frequency high and high for getting the benefit of speed, then at the same time at the high frequency the temperature is going to be increased quite high. So if I take an example of my mobile phone, if we talk about 5 to 10 minutes or half an hour, mobile phone start heat up. So why that heat up? Because of the incoming and outgoing frequency range from the antenna. So we require some thermal management in such a way the heat up is as less as possible. One of the aspect is the leakage current is known as the component that is the undesired and loss of energy, and that contribute in the form of heat. So another aspect, this is from the antenna point of view. Another aspect is from its battery point of view. So if we want a mobile phone that can work for 1 week without recharging again and again, and that can possible if the loss of energy in the form of heat we can manage. So thermal management unit is nothing but they have some techniques how we can minimize the leakage current in the devices, how we can minimize the losses at high frequency, so that we can use the loss of power in the form of heat in the positive application in the battery. Okay, so how those things can be done in the base station, that can be done with the help of composite type of materials. So this yellow part indicates early days these there are so many materials used. We will coming in the next slide on the individual part. So different materials are used for the antenna, mobile phone, its external body. Early days we have the metallic body of the mobile phone, later on they jump to the plastic and ceramic type. So by because metallic having more loss as compared to the plastic and ceramic. So nowadays instead of having single material, composite type material, meta materials, they are used in the these high frequency devices, so that the meta materials are nothing but artificial materials formulated with the different composition of mixture of different materials, and they can tolerate these type of losses, thermal loss and frequency losses. This is the one of the aspect at the base station at our side. Other aspect is from the mobile device support at the user end. We require the mobile devices, their packaging, their filter, substrate, sensors, electromagnetic waves interfacing, shielding. So how these things can be modified. So when I say I have to change my totally infrastructure from 4G to 5G, means I have to change all these things for my device. Base station also, as well as at the user and mobile phone devices also we have to change. So how we can change this? These can overcome the challenges we have in the these devices can overcome with the semiconductor devices with the 3-5 compound. Here at the base station, we can, the challenges we are facing that can overcome with the help of composite meta material type of things, and in the user end type of devices we can overcome the challenges with the help of semiconductor devices. So there are some substrate material that we use early days, mostly PTE type of material, that is poly tetrafluorohydrins type of material used. But this type of material having losses, then people start some other type of composite material, and nowadays the liquid crystal polymer type of material that is highly preferred type of material for the PCBs, because any type of mobile phone or communication devices, they were fabricated on the PCB, printed circuit board, and the printed circuit board are having the both active and passive components, and the material used in the PCB is having a huge impact on the system from 4G to 5G, because the frequency where the frequency involvement is there, material property is going to be changed. Okay, so for that, but we have to change the PCBs from the low frequency to high frequency. Only this can be done by changing the material. And second aspect is, nowadays instead of having a single layer PCBs, multi-layer PCBs are going to be start. So with the multi-layer PCBs, the interference, EMI interference of signal from one layer to the other can be mitigated automatically, or that cannot, we can say, rectified or controlled fully, but they can control up to a high extent with when we say we have multi-layer PCBs. So first layer may have a 10% effect of EMI waves, second may have 5%, and third or fourth may having 1% or less than 1%. So these multi-layer PCBs, they cannot, early days we are having copper material used for the these PCBs. So nowadays not only copper but other materials, like again these PPO, PTEO, these type of material used. Then the filters, as we discussed in the these mobile phones, the filtering of various frequencies is very important. Like we have different bands, like band pass, band stop, low pass, high pass. So these frequency, how we can filter our previous active and passive filters, they are not going to be perform their task in the 5G. So again, though designing those filters, the method remain the same, their circuit designing remain the same, but the thing is, we have to think about which type of material we are going to be use for these filters. So for the 5G, we have another type of materials for the structural and these filters. I'm going a bit fast because we have to touch the divisive part also. So if you feel I am moving fast, I will let me know. I will explain the more detail. If you have any query, you can interrupt me. So from the EMI shielding point of view, where the interference of one frequency over the other is high in the 5G, and that can again overcome with the help of one thing is with the using the, instead of having the one antenna of very high frequency, let's go for the multiple antennas with the shorter frequency for transmission from near by near link. That, and that going to be help with the help of MIMO type of techniques. Another aspect is, instead of having the uh, uh, high frequency of a single device, let's have a filter with the multiple segments. So if we have only one filter, that going to be filter out my noise or undesired frequency, instead of one filter, let me have a segment array of filters, so that the sum of the part noise or em waves or interference can be filtered out in the different stages, so that the end result I am getting in the filter, that can be having the maximum safe signal, and that is free from the EMI interference. And that migration can be possible with the help of different filter material, different shielding material, and different packaging materials. Then RF amplifier and sensors, I am touching so many things. The purpose is uh, all these things required some type of involvement of material and devices, and they require, although RF amplifier and sensors, they are used in the 3G and 4G also. But when we talk about the amplifiers from 5G point of view, then the material change is required. So in the first generation of there are two type of generations in the low frequency, and one generation of the materials in the high frequency generation, that is known as high frequency generation. The first generation, where we have silicon and germanium type of devices, and these silicon and germanium devices are used for the design of low frequency amplifiers. Then when we talk about the 2G and 3G, then RF power amplifiers and sensors are required. And for that we require the gallium arsenide, gallium nitride, indium selenide. These type of materials are used for the devices and amplifiers to propagate the signal. So in the 5G specifically, as compared to 3G and 4G, the power amplification requires a huge as compared to 2G and 3G. Why? Because as I mentioned, the requirement of repeaters or number of towers is huge. So if amplifiers are having sufficient efficiency and gain, then the infrastructure requirement in terms of replacing the antenna nearby in the repeater, that can be mitigated little bit. So if the power amplifier having the double gate from my 4G to 5G, then the, if in a particular area, if I have two towers in the 3G or 4G, and in the 5G I may require 100 or 1000 of towers. But those 1000 of towers, if I have to place in the 5G, then you think about the how much infrastructure investment is there. But that infrastructure, that's why there is a delay in the 5G implementation. So that infrastructure investment can be reduced to half if these RF power amplifiers can be designed with a high gain. So that's why people are thinking about how we can propose these high power amplifier with the alternative materials. Nowadays for 5G base station, gallium nitride RF power amplifier that was proposed, and that is working very well, and that is also not a new task in the search. This was proposed in 2011. One of the USA gave proposed this gallium nitride based amplifier. But the thing is, that is compatible with the frequency match of 5G, but the thing is still the gain is not as we require for the second high frequency band of the 5G. So we have to further improve this. Then that can be possible with the help of the semiconductor fabrication techniques. There are some one of the fabrication techniques in the 5G, we use the LD MOS. So that is the metal oxide semiconductor devices there. LT is the laterally doped MOS. So there are different doping techniques in the semiconductors.
one thing is, I think doping is clear to everyone. Why we do doping? Doping we do to enhance the carrier mobility. So higher the mobility, higher of the carriers, higher will the current in the device, and higher the current, higher will be the speed of switching on and off of the device, and higher will be the propagation. So uh, but this is the positive impact of doping, but the negative impact of the doping is, as we keep on increasing the doping, then there is some losses also in the form of surface roughness, and scattering phenomena take place in the these materials. So ultimately we can enhance the doping into some extent only. So in the nutshell, we can see that the materials for these power amplifier for 5G applications specifically, this gallium nitride material is a very important. So from packaging point of view, we discussed the packaging material for the mobiles going to be changed, and only that purpose is we have to make the shielding in such a way, the losses in the form of heat and uh, other performance in terms of driving capability, that must be as low as possible. Then thermal management we already discussed, we can skip it. So base station, we have also discussed this part. So let's discuss this, the RF application and the operating frequency requirement. So they, from here we can see the different frequencies are used for the amateur radio station, AM radio station, then RFID, FM. So you can see with the different uh, application, we have different range of frequency, and this the air traffic control, weather radar, and some communication satellite, we are using this 2 to 4G frequency. So in these all devices, as the frequency keep on increasing, we have to change the device. Early days we are having the uh, gun diode for the high frequency application. Then we came to the pin diode for the microwave application. So those gun diode, pin diode, they replaced with the HEMT and hybrid type of bipolar transistors. So those are nothing but the replacement of material and structure of a device in such a way they can cope up with the upcoming high frequency. So now we came up to the radio frequency. So from low frequency, when we move to the radio frequency and high, then we have to we have so many add up of the applications like Wi-Fi, Bluetooth, near field communication, radio frequency, RFID. So these applications are going to be add up. So from the this radio frequency type of operations, they were for the previous, we can say 2G, 3G, and 4G. Now for the 5G, we require the millimeter wave type of operation. For this millimeter wave, we have a frequency range of 30 gigahertz to 300 gigahertz frequency, and in this range, if the signals are then there, then we will say this is a millimeter wave. But whole the range of millimeter wave is not suitable for the 5G communication. But we have the two rays of 22 and 28 and 39. So if we use the why we have the different, why we not use the other frequency, because as we keep on the frequency, then the corresponding wavelength that going to be reduced. For this particular frequency, the wavelength is going to be reduced to 10 mm to the 1 mm. So this, because of the shorter wavelength, this is the you can say another way of interpreting that why we are not directly jumping to the high frequency, because with the every high frequency our wavelength will be going to be reduced, and as the wavelength is going to be reduced, then the long term transmission is not possible. Then there are different countries. They have proposed their different standards like this ITU. They have International Mobile Telecommunication Association. In the 2020 they officially launched the 5G, and they have given the range that the millimeter frequency, millimeter wave frequency for from 24 and 74. They are having the spectrum of 17.25 to 5 gigahertz. So the this milliwave millimeter wave range having the different countries had different, and the range I am talking about 28 gigahertz to 39 gigahertz, that was given by the USA, and their Federation of Communication Commission, they have given this range. So why they have already implemented the material and devices requirement for this range, and they analyzed that these gallium arsenide, gallium nitride, that we are discussing, they are highly suitable for the high frequency application, and these devices, they can work best for this frequency range. In the future, after 5 years, 10 years, or 20 years, when the new materials and devices came into the picture, they might tolerate the high frequency. Then this range of 28 and 30 39, that may be increased in the future, and that may be happen in our upcoming 6G or 7G type of technology. For that, we have to wait first for the material and devices that can be used for the technology development. So for this, there are numerous benefits of 5G. We have in terms of milliwave, they having the huge channel bandwidth, that is the 400 megahertz to 1 gigahertz. Then the data rate is also quite high. Then it's also possible to design MIMO type of antennas and other compatible circuits and systems for the their 5G. Then this millimeter wave is not a very new from 5G point of view, but earlier also this was used. But earlier in 1975, this millimeter wave that was used for the satellite and remote sensing. Then in the 1999, this Mercedes, they have proposed for the 77 gigahertz frequency for collision-free avoid self-parking and self-driving vehicles, cars. And military vehicles, they also used as surveillance type of radar for high data rate, that is more than 100 bps for the mobile window. But they are not for the use of public domain, but they are specific for the some secrecy type of military application and some dedicated military vehicles only. So no, from 5G point of view, no, this is, we can say, this range of frequency is available for the public, for the benefit of societal applications. So we have discussed the so many benefits of the milliwave in terms of data rate, and there are some limitations also in terms of their power amplifiers, low noise amplifier, mixture antennas. So all these things we have to replace when we are going to use this millimeter waves for the 5G. So this millimeter wave circuits can be designed with the help of CMOS technology. Now, this CMOS technology is complementary metal oxide semiconductor devices. So early days, these devices were used for the, mostly CMOS devices were used for the low frequency application, for specifically for the digital application like computing system, memory design, microprocessor design, our computing units, mobile phone, computer, laptop. So they are low frequency devices, but here the concern is more related to its computing power. And CMOS technology is highly preferred for the high speed applications, but at low frequency.
But when we talk about the 5G application, we have to deal with the high speed at the same time high frequency also. So for that, we have to combine the CMOS technology with the gallium nitride and gallium arsenide based technology. So they having their separate band of operation, and the Samsung, they in the search they have proposed a 5G based transmitter, and with the help of gallium nitride, and that gallium nitride based material used for the design of p-HEMT processor. So like we having a transistor and NPN transistor, PNP transistor, NMOS, PMOS. Similarly, we have a HEMT, high electron mobility transistor, that is specifically designed for the high frequency applications. So these HEMT, there are some other structures also we will discuss. This specifically designed for the millimeter wave circuit design. So this is the progress of the millimeter wave frequency band in the research, how they keep on increasing from the previous times. As I mentioned, the millimeter wave, they initially in the 1975 for the satellite and remote sensing and automated car was used. Then later on that was cope up with the CMOS technology, and receivers design, transmitter design, their filters design, their bodies design, though can be designed with the help of CMOS technology. But at this moment of time, up to 2001 to 2009, all these were made of we can say silicon based materials. So the millimeter based on the silicon material. So they having the limited frequency application. Then we came up with this mobile and broadcast type of things. When we came up with the 5G type of application and transition, then this first this 5G transmitter was proposed in 2016 only, and this first 5G transmitter were proposed with this millimeter wave with the gallium arsenide based technology with the p-HEMT. So P is the as we know, there are two type of carriers in the devices, electrons and holes. So N type where the carriers are electrons, and P type of devices where the carriers are holes. So this is the high electromobility transistor technology used for the 5G with the gallium arsenide that is proposed in 2016. Although that is functional, but again the limitation is in terms of their gain and their performance in terms of power. The major limitation of these HEMT devices, they are very power hungry. They consume huge power. So as I mentioned, these were used in the early days also for the military and other application. But at that moment time, their systems are stationary. They are fixed at one location, and power is not a concern. Direct three-phase power can be applied. But when we are talking about the 5G type of application, then power is very important point concern. Early days for satellite and military, that is not concerned, but no for 5G. Why? Because now we are dealing with the portable devices, mobile phone and other portable applications. So portable applications must have a low power of operation. But I am saying this gallium arsenide type of HEMT, they are power hungry, they are using huge power. Then how we can cope up with the 5G? Then we have to think other type of material that we will discuss further, that is 5G gallium nitride. So the challenges of the CMOS based things we have already discussed. Their propagation is huge. Their behavior of the material is going to be changed at the high frequency. So with the CMOS technology, with the silicon is not compatible with the 5G. So we have to think about the other. Another issue with the this is the propagation, attenuation, and penetration. So as we keep on increasing the frequency from 3G 3 gigahertz to 100 or 300 in the millimeter wave, you see with the increase of frequency, the attenuation is also keep on increasing.
So this attenuation is nothing but we can say if we transmit a signal in the 3G or 4G, if with the same power of power amplifier, if we transmitting and that is covering 10 kilometer of a distance, and with the 5G with the same power of amplifier, that may instead of 10 kilometer, that may cover 10 meter only. So this is the attenuation. Mean they are restricting our signal in some limited distance only. So if in the one side I am saying 5G is very beneficial in terms of data rate and other thing, but at the same time I am saying its distance coverage is very short. So no, benefits are clear, challenges are clear. How to overcome that we have to discuss. So that challenges we have to overcome with the alternative material and devices. I am repeating again and again, alternative material and devices. So those materials, and we have to first analyze how attenuation take place in the 5G in this range. So the material I am discussing, gallium arsenide and gallium nitride, they are well established nowadays from 5G technology point of view. The circuits and amplifiers, filters, power amplifiers, all those things are designed from the compatible, but they are applicable only in a frequency range of 28 to 38 or 39 gigahertz. That's why we are restricted to this frequency. Although I am saying the frequency of 5G can move up to the 100 gigahertz or 300 gigahertz, because my millimeter wave frequency is up to 3 gigahertz, but I am still restricted to 5G 28 or 38 or 39 gigahertz only because of my problem of material and devices. Again I am repeating, in the future if we have another type of material, if they can tolerate my high frequency, then we can in the 6G or 7G we can think about how we can move ahead. So next in the attenuation, how attenuation take place in the 5G with the millimeter. If the rainfall is there, then the 7 to 10 dB per kilometer distance, this penetration and attenuation is there. Then if the vegetation or plantation is there, indoor building and structure is there, outdoor building and structure is there, then the reflection coefficient in the outdoor environment is there. So all these things are playing a major role in the attenuation and penetration. So how to cope up with this problem? We have to think about some materials, they can absorb these attenuation. So instead of one thing I want to clear here, attenuation is when the signal strikes with some medium, they reflect back instead of moving ahead. That's why they're not going to cover the 10 kilometer distance, they are covering just 10 meter and they are reflecting back. So if I have a material, after reflecting back, they can direct my millimeter wave again in the same direction in which I want, and that my coverage of distance can be huge, and that coverage is done with the help of my MIMO antennas, that is multiple input multiple output. So if the signal is from any side, any direction, that can be redirected again and again with the MIMO. So this is a, you can say, parallel track. So development of material, development of devices, development of antenna, development of other infrastructure is parallelly. If there is there, then only we can implement this upcoming 5G or 6G effectively. So next is the effect of CMOS scaling on the this 5G. So some of the effect we already discussed related to attenuation and other thing. Another is there is the effect of the transition frequency. When we talk about the frequency of the communication, there are two type of aspect of frequency. One is the operating frequency, and another is the transition frequency. So my operating frequency is that we are saying my 5G will operate in a frequency range of 3 to 6 gigahertz frequency, or 28 to 39 gigahertz frequency. This is my operating frequency. My devices, system, antenna, and other all infrastructure associated with the 5G that can operate at this frequency. When I talk about the transition frequency, that is a switching frequency, how my device can switch on and off, that is the transition frequency. And when we talk about the material, gallium arsenide, gallium nitride, then this transition frequency improvement is also required at the same time. But with the 5G operating frequency improvement is there huge, but transition frequency is not as we require. So if we, one of the reported papers there where this amplifier, if we design at 60 gigahertz at this 28 nanometer CMOS technology, then its transition frequency is 250 gigahertz. If I design the same with the most technology with one, they can have 150 gigahertz. So this improvement in the transition frequency is also as important as the operating frequency of my devices. So here we can see this transition frequency, that is improvement take place only five times, whereas this operating frequency, that is improved in the 5G 20 times more. So there is a, we can say there is a gap in the improvement of the operating frequency and transition frequency, and this gap we have to mitigate or minimize. So minimum gap is there, then we can use the effectively all the features of our 5G technology. So let's discuss now on the other part of semiconductor materials. So till now we have any query from the participants?
Only gallium arsenide is suitable for the 5G, sir?
Not only gallium arsenide, there are 3-5 compound semiconductors. So there is a huge range. If you see this particular slide, we have a silicon material. There, this transition frequency is 250 gigahertz for 28 nanometer. If my gallium arsenide is there, this transition frequency is greater than 500 gigahertz. Then indium phosphide we have greater than 700. Then gallium nitride we have greater than 500. So there are different papers are reported on it. So why I am talking about more 5G with the gallium nitride, because this is the more stable combination of the material for the 5G in term of my attenuation. So in the 5G we are talking about the major challenge, major limitation, the long distance coverage is not possible, attenuation is huge, and that can overcome with the power amplifiers instead of replacing. That can also overcome with the antennas also by replacing. But you think I am saying instead of 1 or 10 antenna, I required thousands of antenna in 5G. So infrastructure requirement is huge. Instead of replacing, that is not viable. So we have to think about hybrid type of technology where antenna replacement is also there. At the same time, other peripheral components circuits can also be integrated, so that the hybrid technology came up for the at the low cost, because here the cost involvement is also there. So by cost, if the nowadays we are having the 4G data 250 rupees or for 1 month, or even less for 400 rupees for 3 months. If I have a 5G data and cost involved, I require 1000 rupees for 1 month, no one going to be buy. Everyone say I am happy with the 4G only. Why I invest 1000 for 5G data? But if I am giving the 5G speed, instead of 250 rupees, I am giving 200 rupees, then everyone happy and everyone will jump and migrate from 4G to 5G. So for that, how we can cope up with this cost? Because industry ultimate work for the
revenue generation, and that revenue only can be possible if they invested their whole revenue in the infrastructure only, in the installation of antenna and other things only. Then they are not going to be that is not going to be beneficial from industrial or service provider point of view, as well as the user point of view. So with these materials, silicon, gallium arsenide, indium arsenide, gallium nitride, we are trying to find out the solution for the low cost. So right now, gallium nitride is the only viable solution available for the 5G. But with the time, I am saying maybe some other materials available and the other circuits may be available for the upcoming low cost 5G solutions. So I hope it's clear to you. You have any query? Okay. So these are the materials. Pardon? Okay. So let's continue. So these materials having the different frequency transition frequency, their different resistivity, at the same time having the different mobility, different band gap. So one thing I want to correlate here with these materials with the band gap. So because when I say silicon is not suitable for the high frequency, but gallium nitride is suitable for high frequency, how? Why? That by answer of that by can be correlated from this band gap, because the band gap of silicon gallium nitride, that is different, that is small band gap, but the gallium nitride having the huge band gap, 3.4 electron volt as compared to 1.2 electron volt in the silicon. Due to this high band gap, this material can handle or work or operate at the high frequency. So but the silicon cannot. So early days in the I not remember the exact date, but approximate 8 to 10 years back, ISRO were having a huge challenges in the face of when they're launching the satellite. That was a big news in the media, that whenever they launch the satellite, that going to be failure, and automatically fire is there once they launch the system. What happened at that moment of time, they were in the space, the high frequency radiations are there, alpha rays, beta rays, gamma rays are there in the space. But in the earth surface, those high frequency rays are not there. So if we have a memory design, for example, the memory available in our mobile phone, laptop, computer, so these memories are designed with the semiconductor materials like silicon or germanium, and they are low frequency memories. Same memories, if I apply in the laptop, same memory I apply in the satellite, but that satellite is going to be launched in the space where the high frequency radiations are there, and those high frequency radiations automatically erase my memory, and memory is washed out. But that same memory is working perfectly right in the earth, in our portable devices and stationary devices, but that is not applicable in the space. So application area is very important from the material selection point of view.
Excuse
Then
me, sir. So,
yes.
that failure was mainly due to the erase of the memory, sir?
Erase of the memory. Then they start radiation hardness memory. You just search in the Google radiation hardness memory. You will see in the last 10 years, huge work is done by the ISRO as well as by the other academic researchers on the how memories can tolerate high frequency. Early days there was no problem, but with the high frequency, those memories can tolerate. So the memories nowadays, in the last 5 years, memories are also available with these type of material, gallium nitride and gallium phosphide and helium, because they can tolerate a high frequency. So the device HAMT I am going to discuss in the upcoming slide from 5G point of view. That device is not only designed for the 5G only. That is available from in the literature from last 3 or 4 decades, from 30 or 40 years, people are working on the HAMT and hybrid devices. But at that time, the applications are different from their power amplifier point of view. Like in the 2G and 3G also, we having a power amplifier that is not totally changed in the 5G, but change is in the frequency of operation, change is in the frequency of transition. So we have to change the device structure and material in a such way they can cope up, they can behave well in the same frequency. So if I have a transistor with silicon and IB characteristics, I think everyone knows drain current versus drain source voltage with the different gate voltage, different graphs are there. So those graphs you can get with the silicon also. For a transistor you can get the gallium nitride also, but there is a change in the gain, and that change in the gain is high in the gallium nitride. I hope it's clear. So let's come up with the comparison of efficiency of amplifier of silicon and gallium nitride based. Why we are going toward the gallium nitride from the, because gallium nitride based technology is quite costly. Silicon based technology fabrication is quite cheap and easily. So you know, in the electronics specifically, the cost of product is reducing with time. Every other product maybe cost is increasing, but specifically in electronics, you have a mobile phone, laptop early days 1 lakh rupees required to be invested for 10 or 20 years back. But right now with the 20,000 rupees we can buy a laptop with the even better features 10 years ago. But the thing is, why this happened? Because of the silicon enhancement of development in the silicon technology. So silicon technology is very cheap nowadays. Why? Because there is a natural process in the fabrication. We have a silicon material, they are very cheap. Silicon is nothing but raw sand is there. Sand can be purified and silicon material can be separate out. So available freely, vended available at low cost. So in the fabric, one is cost of material. Second thing is it's designing a fabrication. If in the every device, you know, we require dielectric also. In the 5G also we are discussing shielding, mean EMI waves having huge effect on my nearby other devices. So I have to change my packaging of the mobile, I have to change the casing of the mobile, covering of mobile in such a way those EMI effect must be as small as possible, and those casing must be compatible with the thermal effects also, so that the heat, if there is some heat in the device, my mobile phone going to heat up, that can be transmitted in the environment easily. So that type of things are required. And for those dielectric, if I have a silicon substrate, I can add the oxygen from the external, and silicon and dioxide material, they having a chemical reaction, and silicon dioxide grow automatically, and silicon dioxide is my dielectric material. And that is the beauty of silicon material only. We can grow dielectric material automatically with silicon only. But if I have a gallium nitride or a gallium arsenide, other type of material, I cannot grow my silicon dielectric material automatically. I have to take separate dielectric material and sandwich with the that's why, although efficiency from 5G point of view of amplifier, gallium nitride having the huge efficiency as compared to silicon, but still people, we can say 80 or 90% power amplifier, they are still designed with the silicon instead of gallium nitride. Why? Because of the cost involvement. Another benefit from gallium nitride technology from 5G point of view, the operating frequency of the gallium nitride based technology, that is keep on increasing. So gallium nitride material used for the 3G and 4G application also, but with the next generation 5G and even 6G, 7G, their frequency, this axis shows the frequency. So this material can handle up to 100 gigahertz of frequency. So their properties, when I say my gallium nitride can work for 100 gigahertz and silicon cannot work up to 100 giga, my mean to say its behavior at this particular frequency is remain the same, but the silicon material, their behavior change from its IB characteristics point of view. So drain current characteristics remain the same in gallium nitride, but in the silicon, the current can be in the zigzag path instead of a straight line. There are some other 5G application with the gallium nitride of material. They are they can one thing is they can cope up with the high frequency and the requirement of 5G frequency 3 gigahertz to 6 gigahertz, and this range 24 to 50 gigahertz. So this is the range for millimeter wave. So this type of material can compatible with the both 5G proposed frequency range. So these type of also having ultra band wideband linearization. So 5 MIMO antenna and beam forming, this is also compatible. So MIMO antenna, I think everyone aware, multiple input, multiple output for the different signal transmitter. Beam forming is also one of the same type of method used for the 5G, where if there is some attenuation or penetration is there in the signal, that can be reboosted with the help of beam forming, so that the number of users can be covered large. Then the low voltage, small size, high linearization, these are some of the other features with the gallium nitride. So early days, when I say gallium arsenide and gallium nitride used for the military application, then they are using huge power. But for my portable, I require the low voltage operation also. And this is still a challenge, because if I design this gallium nitride based 5G high power amplifier with the design at the this low voltage, then its gain also reduced. So but that is not acceptable. I have to improve the gain also. So this is, we can say, still under the search how we can improve the gain also at the same time when we are reducing the power. Then it's small size and high temperature handling capability, higher reliability. So these are some of the other aspects of gallium nitride from the 5G point of view. So then gallium nitride enabling some solution for the 5G. So high density, as I mentioned. So with this P HEMT, high electromobility transistors. So if we have this was designed in the 2002 with the gallium arsenide type of material. Okay, so same scale to the smaller dimension. So if this is designed suppose at 0.25 mm technology, millimeter technology, then this is designed with the 0.15 mm. So this scaling is there in the dimension, reduction in the dimension. So scaling is always beneficial to make the thing portable as small as possible. But again, the question is, we cannot scale drastically from bulk to nano. If we talk about the digital application or from low frequency application point of view, people are talking about the 10 nanometer devices, even your mobile phone for the memory application having the FinFET based 10 or 16 nanometer devices. But when we talk from the high frequency requirement of view from 5G application, we're still stick on the micron technology or millimeter technology. So at that time we require the high size. Why? Because if again the effect is in terms of EMI and frequency degradation point. So scaling is still there, but with the gallium arsenide it was not possible to scale further. Then people migrated to the HEMT, same device but with a different material, with the gallium arsenide. Gallium nitride replacement of this. Then this was done in the 2014, and this is still applicable for the 5G, and people are working for this technology of gallium nitride technology to reduce the size and complexity, and this is commercially available in the market for the 4G application and upcoming 5G applications. So till now we have discussed the most of the things related to 5G and material devices. Now next I will discuss in brief about the 3.5 semiconductor devices, how these devices can work, how they can be used for the 5G application. So there are three type of major 3.5 compound device. So one of the participant asked by gallium nitride only for the 5G application. Is the gallium nitride only? I said no, but at the same time I have justified it also that gallium nitride is best for the this frequency of range. So here another way of saying the same thing for 5G, not only gallium nitride, not only the Hampton device, there are some other devices also like MESFET, heterojunction bipolar transistor, and Hampton transistor. So these devices are available for the they can use for the 5G application. But again, first we have to identify for which application, for which circuit I am going to use these type of devices. If I am designing my power amplifier, then this HAMT is suitable with the gallium nitride material for the 5G application. If I am using this for the filter or some other as compared to HAMT. So there's not only one parameter of selecting the material for the 5G. There are multiple parameters. Those parameters involved in terms of this performance, in terms of speed, performance in terms of frequency, performance in terms of temperature handling, performance in terms of its shielding and tolerance in the environmental EM waves, and at the same time very important aspect is its cost involvement of material, also cost involvement in the fabrication also. So by gallium material we have already discussed, so it can tolerate the having the high breakdown of the field, so it can handle a high frequency. Then the peak of velocity is also high. Then the energy band gap is high, that's why they can operate at high temperature also. Then the conduction losses are less in the own resistance. So there is a comparison in the performance of these three devices, MOSFET, MESFET, and MODFET. So with the different gate voltage, if we see the drain current, then these operate at the different voltages and different temperature. So accordingly we have to identify where we are going to employ these devices. So this is the gallium arsenide based MESFET structure. So this is how we fabricate this gallium arsenide with the different layers. So with these this gallium arsenide MESFET can also work in a frequency range of 3 to 30 gigahertz. Okay, so in this range how we can modify this structure if we have to cope up with high frequency. So we have to change this gallium arsenide material as a conducting material. At the same time, it's interconnect at the source and drain, and it's a passivation from the other. This is the single device, but you know, in the amplifier we require the large number of devices, and they have to be isolated from each other. So for that also we require the dielectric material. So this is the silicon based devices, and this is a gallium arsenide based device. So then the MESFET operation is of two type. One is the depletion mode type and enhancement mode type. So we can skip these basic things. So as we are close to 1 p.m., let me skip some of the slide and come to why we have the Hammett structure. So okay, let us discuss this in detail. Performance comparison of MESFET, HEM, and heterojunction bipolar transistor. So with this comparison, we can find out why gallium nitride based material or a different, how we select a particular material or device for some application. So if we have a this HBT type of device with the heterojunction bipolar transistor, the speed is high, and this is the transistor frequency, and mass effect having the low frequency. It's HEMT has the moderate frequency, and HBT having the high frequency. Now if I compare the gain and bandwidth, then the gain is high in the HEMT and this device. Then the phase noise, that is low in the HBT, but the noise is high in the HEMT. Then the ratio of the gain, then that is high in HBT. Then it's if I say threshold voltage, then the since the large signal handling in term of collector efficiency and power density. So these parameters, based on these parameters, we have to identify which device we are going to be used for the power amplifier or filter material, or for my MIMO or other type of techniques for the 5G. So here I want to convey message that there is no a single parameter, there is not a single material, there is not a single device that can handle all my requirements of the 5G. So then there are different type of leakage current in the devices that contribute in the heat, and there are some remedies also how we can remove. So in the detail we cannot discuss, we are already running out of time. So let me discuss a bit about the okay, this part I would like to discuss. If I am saying we have a different materials, different devices, there is no single parameter, there is no single material, there is no single device that can applicable for my 5G. Then how I can select a material, how I can select a device for my 5G application, for other applications. For that we have the methods for the device modeling. So with modeling we can analyze the performance parameters of materials, performance and parameters of the devices, and come up with the conclusion that okay, this is the best material for my this frequency, this is the best material for my this segment of frequency. So for that we require 2-3 different methods. One is the measurement based on some experimental setup. We have a 4 probe station type of setup, with which we can analyze the material properties. Physics or chemistry people, they might be know much detail about the SEM, TEM, scanning electron microscope, to analyze the properties of material experimentally, how they behave at the 5G frequency, how the same material behave at the 10 gigahertz frequency, how same material behave at the 100. So experimentally we can analyze. The same thing we can analyze with the help of TCAD modeling and simulation tools also. So for that we require the device level simulator tools like Silvaco, Centaurus. So those devices can be designed and fabricated in the virtually with these tools, and we can analyze their behavior. Another thing is the process technology that is related to fabrication. So because when we write a code or simulate something in the tool or with the MATLAB or Silvaco or Centaurus, but we get some results, but the thing is that results are acceptable or not, how we come to know. So for this, that validation, we require a set of the experiment data that is provided by the foundry, and we have to compare our simulations with that standard parameter so that we can say our this material, whatever the result we're getting, they are acceptable. So that can be done with the fabrication process also. Again, fabrication can be done experimentally and virtually with the tool also. So in the Silvaco, there are two parts. One is the Atlas and other is the Athena. So Athena part deal with the fabrication of devices. So experimentally fabrication facilities in India are very few, but with the help of tool we can fabricate and analyze. So now we have a three set of parameters, one with the measurement or TCAD simulation by designing or with the fabrication, and that can be compared or modulated with the physical compact models, and the end product can be designed with the help of these modeling technique. So with this method, basically this is the way how we can bridge the gap in the device model and the integrated circuit for the various application. So there are various type of modeling methods. So I think that we can skip some of the part. We are already running out of time. So let me come to. Okay, this part I would like to discuss briefly. DC measurement of aluminum gallium arsenide and gallium nitride. So if we have a device with the gallium nitride or aluminum gallium nitride, so how we can analyze it experimentally. So this is the four probe station that I am discussing experimentally. We can analyze its IB CB characteristics, and once this experimental setup can be interfaced with the source meter and with the some software like ICCAP or Silvaco or Centaurus. So experimental analysis, TCAD tool analysis, that can be compared with the help of some plotting tools, and then we can summarize that, okay, this is the best material, this is the best device for the range of frequency we required for the 5G or 6G or higher upcoming technologies for communication. So with this, I like to summarize what we discussed in this lecture. We started with the 1G to 5G evolution, how with the change in the frequency, change in the parameter and other setup, we are migrating from 1G to 5G for the high speed, high downloading, uploading, and data handling capacity. And what are the opportunities, challenges, what are there, and how we can mitigate those challenges with the help of alternative materials, alternative devices. So new materials requirement is there for 5G, and right now in the literature says gallium arsenide, gallium nitride are the best for the 5G application, but in the future upcoming technologies, alternative materials, new materials maybe come up. So 3,5 compound semiconductor materials are suitable for high frequency application. Specifically, if we talk about the power amplifiers and 5G filters designed for 5G, so these 3,5 compound materials are there. So in these, one of the important aspect is the thermal power management, and that thermal power management can be done automatically with the help of MMSC, that is micromillimeter wave integrated circuits. Then leakage current aspects, although we have not discussed in that detail, these we have skipped some of the slide. So in nutshell, we can say there are some methods by which we can reduce the leakage current and enhance the performance of a device. Then the HEMT, we have discussed briefly, that is the much suitable for the high frequency, although there are some other structures also there, but HEMT is from 5G application point of view. HEMT with combination of gallium nitride is the viable solution for the 5G application. So with this, I thanks all the participants for their patience listening. So if you have any query, we can discuss, please.